Okay, so this is a lecture in 341 random processes. Last time we were talking about mixed random variables. This lecture's focus is going to be on probability models of derived random variables. If you're following along in the book, this is chapter 6, sections 6.2 to 3, somewhere around in there. These are probability models of derived random variables that are continuous random variables. We had looked at derived random variables for the discrete time case earlier in the semester. So the basic idea here is that we would like to go ahead and create a new random variable y that is going to be some function of a known random variable x. So we have a real simple model here that y equals a function of x, and because x is known, we know the PDF of that particular random variable, and so we'll call that fx of x. We would like, using that knowledge of fx of x and the mapping function g of x, to find the probability model for the derived random variable y. So what we want out of this is we would like to find the probability density function fy of y using this information. The method that we're going to employ here are real similar in flavor to what we did for discrete time. We'll do some examples to illustrate it, but it's a CDF-based method. So the first thing you're going to want to do is you're going to want to find the CDF. So we want to find the CDF of y, which is really to say that we want to find fy of y, which is equal to the probability of y less than or equal to y, right? And then the second method in here is that the probability density function fy of y is just the derivative with respect to that random variable y, right, of the CDF fy of y. This is a real simple to state technique, and by itself, just stating it doesn't really show us how to make it work. So it's definitely one where I think doing some examples is going to help us out, just like it was in discrete time case. So let's take a look at two common cases. So we'll take a look at two common cases in this particular case of finding derived random variables. So two common cases. The first one that we're going to take a look at is if we have a random variable x. So I'm going to take a random variable x. I'm going to go ahead and, for this particular example, constrain myself with a real positive constant a, so some a greater than or equal to 0. And then I'm going to create a random variable y, which is just a scale of x. So we're going to scale x by a non-negative parameter a, and I would like to find out what the probability model of y is. Using the CDF method, the first step in here is to find fy of y. So I'm going to go ahead and write that out. The CDF of y, cap fy of y, right, is equal to the probability that cap y is less than or equal to little y, something along those lines. And the method here really is just taking our mapping function, substituting that in for y at this point. So we know that y is equal to a times x, right? So we can plug in a times x for y, and that's less than or equal to some particular observed value, little y, right? That little y is just a value. Here we're going to go ahead and solve for x. So this is the probability because a is non-negative. Part of the reason I constrained it there is so that I'd know what to do on this next step. Divide by a non-negative number a, and I'm going to get x less than or equal to y by little a. Well, that is already in a form that we understand. This is now in terms of the known random variable x, right? And the probability that x is less than anything is equal to its CDF. So this is fx of not little x, but of y by a, something along those lines. Once I've got that, right, we know that we can go ahead then and do the second step, which is to say that the probability density function fy of y, right, is just going to take that CDF value, which in this particular case is f of x, y by a, and we are going to differentiate that with respect to y. So I would go ahead and here do a ddy of, well, we said fy of y, but we know in this particular case that fy of y is cap f of x, y by a, something along those lines. Turns out we can do this without even knowing the distribution of x. Any derivative of a CDF, right, just gives us the PDF. So I'm going to get little fx of y by a, and then I have to differentiate that argument. This is just the product rule in there. And so the derivative of y by a with respect to y is a 1 by a, something along those lines. So I get a couple of nice results here that I'll just clean up in a little bit neater way. My derived random variable y's CDF, right, can be gotten from the known CDF of my known random variable x, and that's just fx of y by a. And then we saw further that the probability density function fy of y, right, is just a scaled version of the probability density function of x, so fx, but using the variable y by the scale factor a, something along those lines. I'm going to go ahead and block those guys up, and we will think of a real simple example in this particular case. So let's just, as a really quick example, take a look at a random variable x, and we're going to go ahead and look at its probability density function fx of x. And in this particular case, I'm just going to go ahead and do a uniform 0 to 1, so it's going to have height 1 type of characteristic. We've seen this guy before. We had first looked at uniform random variables when we introduced the idea of continuous random variables. If I did the CDF cap fx of x, right, we know that that's going to just be 0 up until we start getting some of that probability. It's going to increase linearly, and then after 1, right, it's going to plateau out at 1, something along those lines. So we know what those guys are looking like. This is all part of some example that we're working on in here. I might go ahead then and say that I'm going to create a new random variable y equals, how about 2 times x. So I'm going to be multiplying x by a factor 2. This is stretching, right? So here we have a greater than 1, and that really corresponds to a stretching type operation. So we're going to stretch that number of values out so we get a larger range. It's going to stretch the probability density function as well. And what we had from our previous result was that fy of y, right, was equal to what? 1 by a. A in this case is 2, so I'm going to get a 1 by 2, so I'm going to get a half, and I'm going to get little fx of, now put in for the argument here, y by a, so y by 2. So if I take a look at this and I want to sketch it out just a little bit, I can certainly do so. I'm going to go ahead and give myself the axis in here. This is a function of y, and I'm trying to plot out fy of y, something along those lines. Fx is what? F of x is, if I just continue this, I'm going to get a half times whatever f of x is. F of x is going to be what? Well, we knew it was 1, right? When the argument, right, in this case the argument is y by a, of course that I guess I could put in as a particular in this case of 2, so let's go ahead and make that a 2. So y by 2 is squeezed between, when the argument is squeezed between 1 and 0, it was uniform on that interval, and it was 0 otherwise. If I clean this up just a little bit and multiply that 1/2 in there, I'm going to get a 1/2 for what? Well, if I take a look at the range of support here, 0 less than or equal to y by 2 less than or equal to 1, multiply everything by 2, I end up getting it in a little more standard form. I'm going to get 0 times 2 is still 0, less than or equal to y, less than or equal to 2 times 1, so 2, something like that, 0 otherwise. So we do get exactly what we expect. We're getting a stretching type of operation. The values no longer go from 0 to 1, they go from 0 to 2, and so I can go ahead and get that. I still have a flat distribution here, right? It's still uniform in shape in this particular case. It's just going from 0 to 2 in this particular case. We know that a probability density function has to integrate to 1 because I stretched it out, right? It's over a wider area. It better have lower height, which is why that factor of 1/2 came in there. A quick mental math check on this guy definitely shows that this has all the properties or characteristics we want for probability density function. It is non-negative, it is something that integrates to 1, and it does have that relation that we expected given our mapping function to get y from x. If you recall, y was just equal to 2 times x. If x went from 0 to 1, well then y is going to have to go 2 times that, so 0 to 2, and that's exactly what this result shows. Another example that we can do, so we were looking at these different examples. The first example we showed was a simple scaling type of operation. We're going to move to another example. So let's do as another example that we have a random variable x, again known in this particular case, and I'm going to create a new random variable y as being equal to x plus some real constant, some b. So this is a shifting operation. We should be moving things around. We'd like to be able to go ahead and get the probability model for this derived random variable x. The probability model for this derived random variable x can be gotten from the CDF method. And we just start out by writing the CDF of y. Fy of y is what we want. That is the probability that random variable y is less than or equal to little y. This wouldn't get us very far, but we know the mapping function that relates x and y. So I'm going to just substitute that into this expression. Y is just x plus b, all being less than or equal to now little y. And I can write that out as a probability that x, right, is less than or equal to y minus b. This is exactly the form for the CDF of x. And so I know that this whole thing is fx of not little x, but of y minus b. We do need a function of y coming out of this, right? Because cap f of y is a function of y. It's just being related to a known quantity, the CDF of x in this particular case. So we shifted our variable x by an amount b to create our new variable y. And what we find out is that the CDF itself just undergoes a shifting type operation as well. If I want to finish the case out, so I find the probability density function, f sub y of y, little f sub y of y, we know that that's the derivative with respect to y of whatever our CDF is, fy of y in this particular case. I'm going to go ahead and plug in what is fy of y. So this is ddy of fy is just fx, right, of y minus b. The derivative of a CDF does indeed give us the PDF, so I'm going to get little fx of the argument y minus b, and then I need to take ddy, if I show out the step, ddy of y minus b. You have to differentiate that argument as well. This is basic calculus. Well, in this particular case, I just get fx of y minus b, right? Ddy of y minus b is just 1, so I just am left with the result fx of y minus b. It is exactly what we would have expected. I shifted my random variable x to give me a random variable y. What I find is I get a corresponding shift in the probability density function as well. I also saw that I got a shift in the CDF. So to just demonstrate this with, again, a very simple and trivial example, let's go ahead and have fx of x as being equal to a uniform random variable. Let's go 0 and 1 again. So it's going to be a uniform random variable on the interval 0 to 1. Go ahead and draw that out. X on the horizontal axis, we have this probability density function fx of x on the vertical axis. It's going to have a uniform value of 1 on the interval 0 to 1, something along those lines. I'd like to create a new random variable y as a transformation of this particular random variable x. And so I'm going to go ahead and make this particular guy, how about let's make it x plus 2, something along those lines. So I'm going to be adding a value 2 to my value x and seeing what I get for an overall distribution in this case. Well, we had gone through all this effort before, and we saw that the end-up distribution, we had fy of y. I guess I could have written it down here as well. Fy of y is just that fx of y minus b. So I have fy of y, right, as being equal to fx, right, of y minus, and b in this particular case, if we go back up to the original that we had looked on this, we had x plus b, and we ended up getting a y minus b. So we had an x plus b, x plus b, x plus b. So my b here is 2. I'm just going to go ahead and plug that in. I'm going to get y minus b, so I'm going to get a y. Whoops, let's put that back down. We will end up getting, in this particular case, a y minus 2 in there. Now we just have to be able to plot that out. What is f of x? We know f of x is something that is 1, right? Over the interval, we can see it over here. It's over the interval 0 to 1. So whatever the argument is, the argument in this case is y minus 2. So when it's sandwiched between 1 and 0, I get 1, and it's 0 otherwise. I'd like to clean this up into a more familiar form. And so if my piece will just cooperate a little bit here, this guy is going to be equal to, and I get a 1, add 2 to everything that's going on over here, right? So add 2 to all those pieces just to get it in a more familiar form. So 0 plus 2 is going to be 2, right? Y minus 2 plus 2 is just going to be y, and 1 plus 2 is going to be 3. So I find out that I get something uniform on the interval 2 to 3. That's just 2 away from what it was before. I just shifted everything over So we started going between 0 and 1, and now we're going between 2 and 3 because all we did was add 1. We're picking easy examples right now, right? So this is nothing that's too surprising, easy to visualize in this particular case. So the results should be making some real intuitive and simple sense. We will want to work towards some more sophisticated ones as well, some more sophisticated examples. Let's try one of these now, actually. I'm going to work on an example that is going to confirm a result that we had seen before. So if you recall, previously we did something like this. We said, hey, let's take a look at a random variable x that is distributed as a normal random variable, and let's let that normal random variable have some mean mu x, and let's let it have some variance sigma x squared. So this is just a regular old normal distribution. We had come up with a result that we did largely without proof at the time, where we said, hey, if I take y as being this kind of simple transformation of x as being ax plus b, so scale and also shift x, we had made some observations about that. One of the things that we said was that the mu of y, which is expected y, right? We knew that we could say that that is expected, put in what is y, that's ax plus b. We know how expectation works. That's going to be a expected x, right, plus the expectation of a constant b is just that constant. That's going to give me a mu x plus b. So finding the expected value, that first basic statistics is really straightforward. We also know that there was this idea of variance of y, right, is going to be the variance of ax plus b. Shifting doesn't affect variance, but multiplying by a scale factor, we derived this in class, should have given us an a squared variance of x. So these were ones that were real easy to get. The one thing that we didn't prove when we finally did all of this is we said, okay, we got the mean and the variance. We said that this is also this combination, this thing that says that y is equal to ax plus b, that combination comes out as being distributed as a normal. So we said something about the resulting distribution also being normal, and then we just put in what those particular mean and variances were that we had calculated before. So we know that this thing is a normal. We already figured out what the mean was. That's a mu x plus b, and we know the variance was an a squared, right? Sigma x squared, something like that. What I would like to focus on right now is really showing that this new random variable y, right, is distributed as a normal. That is a derived random variable, and I want to find out or show that its probability model does indeed follow the normal model, the one that has that normal probability density function. So we're going to try to use the Cdf method for this as well, and so I'm going to be looking at my fy of y, and I know that that is my probability that y is less than or equal to little y. Go ahead and plug in what is y. This is the probability that ax plus b is less than or equal to little y. And we know that we can do a little bit of algebra here so that I can get cap x all by itself on the left-hand side. So I would subtract b from both sides, right? So I'm going to get if I look at this, a y minus b on the right-hand side, and then I would have had to divide by a to get x by itself. So I'm going to have a y minus b by a, something along those lines. So the CDF here of y turns out to be looking just like the CDF for x, which for a normal random variable, we know exactly what it looks like. The CDF is going from where things start, so minus infinity in this case, to whatever value we are interested in finding the CDF point up to. So in this case, that's little y minus b divided by a. So I'm going to be going upper limit on my integral here, y minus b divided by a, something along those lines. And then because we are looking at the probability of x being less than all of that stuff, this is the CDF. We know that this guy is the CDF fx, right? Just at that y minus b by a, something along those lines. So the CDF is based on what? We put in the probability density function for x, because x is known to be a normal. We know exactly what that CDF looks like. We're going to have a factor 1 by root 2 pi. There is a sigma x down there, and then we have an exp. And in that exp's argument, I'm going to get a minus 1/2. And then I'm going to have a quantity here. I'm going to make the variable of integration here something just convenient, so I'm going to call it u minus mu sub x divided by sigma x quantity squared. And for whatever reason, we're going to get rid of that. And then I'm going to have my du in here. Got it a little bit squeezed over. I'm going to try to move this a bit on the other side. So let's take a quick look at this, just make sure we have it. CDF is just an accumulation of probability up to some particular point. So we knew that point was y minus b by a in this particular case. This piece right here, right, is just nothing more than the probability density function. It's a probability density function for a normal mu x comma sigma x. And you can look that back up from the previous notes or go to the back appendix in the book. It gives all these probability density functions for various families of random variables. Okay, well, we still have a little more work to do here. It's not totally obvious that this is helping us just quite yet. I would like to get this into just a little bit more of a convenient form. And so I'm going to end up doing a variable substitution in here. I'm going to go ahead and let, in our particular case, v equal, and I'm going to do an au plus b. And I know my dv then is going to be equal to a du, something along those lines. This is, if you want to think about it, a u equaling v minus b by a. If I solve for my u parameter, just this one resolved in a different way gives us that. And if I continue with that a little bit more, I can also try to compute out what the limits of integration what the limits of integration are going to be for this particular change of variable as well. So let's just see if we can work on this. So we were still getting fy of y, right? We have an integral. That integral limits we will worry about in a minute. I have to have still in there a 1 by root 2 pi, something along those lines. There's still that sigma x in there. Got that guy going as well. I have my exp. And I'm going to have a minus 1/2. And what were we doing? We had u, that u up here, that was this one in here. And I'm going to be replacing u with that quantity right in there. So I need to make that substitution. So I'm going to give myself a little bit of space here. I'm going to have a v minus b by a. And then I'm going to subtract from that mu sub x, divide by sigma x, right? Quantity square that guy, something along those lines. And then I need to put in what was the differential element, du, but in terms of dv, and we know that that is, taking a look back over here, du, solving for du, I'm going to get du as being dv by a. So I'm going to put in here dv by a, something along those lines. And I should be able to almost get this thing finished out. So previously we had a variable of integration, right? That was this u guy. We're changing that to this v guy. And so I need to change my limits of integration to reflect this new v variable. And I think the utility of all of this will become apparent pretty dang quick. So the lower limit, if you remember, the lower limit was minus infinity. If I put minus infinity into for u, doesn't matter what a and b are, v is also going to be minus infinity. So my lower limit here will stay at minus infinity. No particular problem in there. If I look at the upper limit that I had in there, upper limit was u equaling y minus b by a, and I would like to take that particular guy and again solve for what's the corresponding value of v in there. So go ahead and plug that particular guy in there as well. I'm going to have a times the quantity y minus b by a. The a's will cancel. I'm left with a y minus b, and then I'm adding a b to it, and so I'm left with just y. And that's really the reason I chose this particular transformation, because now I'm getting something that is an integral from minus infinity to y. That's looking a lot more like a CDF, right? A CDF of y should be an integral from minus infinity to y of whatever the probability density function is. So I'm hoping what's left over on the right-hand side looks like the probability density function for a normal with the known mean and variance that we had computed out before. So I just need to do a little bit of cleanup on this. So I'm going to continue. I have an integral now, minus infinity to y, and I have, in this particular case, again, if I take a look over here, there was this lone a out here. I'm going to move that a over there with that sigma x just because I happen to know where I want to go with this. I have a 1 by, and I'm going to have a square root 2 pi, something like that. and then I have an A sigma x, which by the way is the standard deviation of y that we had been working on as well. We'll go back and check that out here in a second. We have the exp then, and I'm going to have my brackets going on in there, and then I've got to figure out something about how to simplify this next piece as well. If I work with this just a little bit, I probably can end up taking this overall expression that we had here, and I just want to get it into a little bit simpler form. If I multiply the mu x by an a by a, that's just a fancy one, then I can do some simplification on this, and what I should be able to get, I still have the minus 1/2 out front, that's no problem. I'm going to have a v minus b minus, right, mu x by a. So I'm going to have a v minus b minus mu x times a. And then all of that would be divided by a, which can be brought down to the overall denominator. That's going to be an a sigma x. Just a little bit of algebra going on there. Squared go out, and then put a dv on this as well. Okay, so almost there. Just about got it. This is still my fy of y. That fy of y is equal to an integral minus infinity to y. And I'm going to have a 1 by, I'm going to do a little grouping in terms here that are familiar. I'm going to have a 1 by root 2 pi, and I have an a sigma x that I'm going to group together. And I have an exp, and I'm going to have my minus 1/2, and I'm going to have a v minus, and this v minus is going to be something like an a mu x plus b divided by a sigma x. That whole quantity squared ended out. Ran out of space here, so I still have that differential dv sitting in there, something along those lines. Well, what does this look like? This whole piece here looks exactly like the probability density function. This is the probability density function. It is what? We have a 1 by 2 pi, that's normal. Here is my standard deviation of that particular normal distribution. See the same standard deviation over there. So this is a PDF of a normal we're working on. The standard deviation was a sigma x. So usually we put that normal in terms of its variance. So we just square that standard deviation, something like that. And then what is the mean in this particular case? The mean, right, is the stuff that I subtracted from the integration variable in the numerator, that exponent. And so we see that's a mu x plus b. So this is a normal a mu x plus b mean, right, and variance a squared sigma x squared. Well, that's exactly what we had come up with previously when we just used our basic rules of expectation and variance. We had seen that the expected value of y did indeed have a mean a mu x plus b, that the variance of y did indeed have that form of an a squared variance of x, which gave a standard deviation of a sigma x. The only thing that we needed to show was that it was distributed as a Gaussian, and we did that through the CDF method, and just noticing that, hey, what we were left with here when we did the CDF was we got something that absolutely looked like the probability density function of a normal. If it looks like a normal, if it speaks like a normal, well, then that guy's a normal. And we see a nice confirmation in this particular case that we got out the mean and variance that we would have expected. So a little less trivial example, it's still pretty straightforward, where we took a particular distribution, in this case a Gaussian, we applied a transformation ax plus b, and then found out that indeed what we got out of that is exactly like we expected. We also got a Gaussian coming out. So you do that linear transformation of a Gaussian, it stays a Gaussian. So we're still doing pretty simple stuff at this point as far as what kind of derived random variables we're doing. The next one is going to be a definitely much more involved example. So let's see if we can, in this particular case, transition to something that is more challenging, something that's not quite so trivial. This next one is going to be a more involved example. And just because it follows nicely, might encourage you to do a little reading in the book. I'm just going to say that this is a form. It's kind of like a generalized version. It's a generalized version of example 6.4 in the textbook, something like that. So I'm going to take one that they did a specific case for, and I'm going to solve it in a more generic way. This more involved example, I think, will be instructional, just to see that these things do get a little bit complicated, and you do have to keep your wits about you in order to get a right answer. So for the time being, I'm not going to worry about what is the distribution of x. We're just going to assume that we have it. So we will assume that we have a known, right? We have a known random variable x, and we are going to create a derived random variable. So we're going to let that derived random variable y be equal to some scale, but it's not going to just be multiplying x, it's going to be multiplying x squared. And I'm going to go ahead in this particular case consider the case where that scaling constant is a positive real number. So we're going to take x and square it, right? And then we're going to scale it by a c. It looks a little bit like the first case we just did earlier at the start of this lecture when we were talking about just scaling a random variable, but we're scaling the square of the random variable. And that squaring absolutely complicates this particular example quite a bit, actually. So let's take a look at the event. We're going to take a particular look at an event of y being less than or equal to some little y. That's the event that we need in order to find the CDF of y. If I want the CDF of y, I have to know what happens when y is less than or equal to some particular value. Well, that event occurs in terms of the x value, right? It occurs if that particular x parameter is between minus root y by c less than or equal to x less than or equal to root y by c. If you wonder where we get that, we just have to draw, and these sketches almost always help us, so I'm going to go ahead and put a sketch in here. I would like to look at what happens with different values of x to generate values of y. What do we know our mapping function was? Y is equal to some cx squared. C is a positive real quantity. X, it could have been plus or minus, but when you square it, it absolutely is going to stay positive. So I have a positive quantity here, positive quantity there, and that means that y is always positive. We know that, okay? Whatever value of x's I have, I'm going to square them and multiply them by some c to give me y. Everybody should recognize this particular kind of an equation. That's just a quadratic equation. It's a quadratic equation that intercepts at the origin of the xy axis. So I'm going to get something that looks like this, right? Get a quadratic. It's a convex open quadratic equation, something along those lines. That parameter c just changes the rate at which that guy goes. So I'm trying to figure out this event. The event here that we're looking at is y being less than or equal to some little y. So I'm going to take a value, little y. Here's my value, little y, okay? And I'm interested in y. I probably should have called this axis up here, maybe a cap y, something like that. I'm going to be looking at cap y being less than or equal to little y. So I want to know what's the cases where y, right, is at some value or lower. Well, what values of x can give me a value y that is that little y or lower? We can see the intersection points here, right? The range of values x that map in this particular case. Again, I probably should have used here a capital X, maybe something like that. So I'll go ahead and put my capital X over here. And we have some, what is it, little minus x and plus x, something along those lines. Anything between minus x and x, right, is going to be squared and give me a value y through that function cx squared as being y. So that parameter c comes through in the parameterization of this curve, right? Something like that. So if I want to solve on this, I know it's both plus and minus values of x that do that, right? And if I know my original mapping function, it was y equals cx squared. Let's just solve for the x. That's going to be x squared, right? This goes to x squared being equal to y by c. Take the square root of that guy. We know that x is going to be equal to plus or minus square root of y by c. And that's exactly, whoops, that should have been a c. Y by c. That's exactly what we had said up here, right? That event, that y is less than or equal to some little y, is just going to correspond to values of x that are on that interval that go from minus root y by c to plus root y by c, something along those lines. So we can visualize this through a little picture, and we can also just get it through the mapping function as well. Okay, So what in the heck are we going to do with this guy? Well, it's a critical component for us when we work on this CDF method. We're trying to find the distribution, the way that this random variable y is behaving, what kind of model it behaves according to. CDF method says let's find a CDF of y. So Fy of y is equal to what? It is the probability that y is less than or equal to y. That's the event that we just talked about. But we, through our pictures and just knowing that transforming function, we know that that's the probability of what? We know that that is the probability in this particular case of cx squared less than or equal to y, which by that picture we know looks like the probability that minus root little y by c is less than or equal to little x is less than or equal to root. And in this case, we are going to have, that shouldn't have been a little x, that probably should have been a capital X. If I can get this guy to erase, that we get that guy x less than or equal to then little y by c square root on the right-hand side, something like that. That's not exactly in the CDF method, or not exactly the CDF of x, although you could take it as a difference of two CDFs potentially. Well, let's see if we can take it to the next step. This little thing was my what? Fy of y, something along those lines. And so I would like to go ahead and be able to work with that. If I did this just as a probability, I could do it as CDFs, a difference of CDFs, but I think in this particular case, it's easier just to write it in terms of what it is. A probability over an interval says go from your lower limit, that's minus root y by c, to the upper limit, which happens to be root y by c again, and it's probability involving x, so we're going to have some fx of x dx, something along those lines. That is my Fy of y in this particular case. So I'm still trying to find the probability model. We usually do that as the probability density function. So I'm looking for Fy of little y, and I know that that's just the derivative of my CDF. So I'm going to do a ddy of Fy of y, which is going to be a ddy, right? In this particular case of, I'm going to put it in here, an integral minus root y by c to an integral upper limit of root y by c of fx of x dx. And just a reminder in here, we do know that the y here is always greater than or equal to 0, something along those lines. Well, I need to take the derivative, right, of an integral function. In the most general kind of case, we could take the derivative with respect to some variable, and that variable might show up in the limits of integration. It could also show up inside the argument of the integral as well, even though it doesn't in this particular case. There's some calculus math techniques that certainly help us. My hope is that you saw this back in your calc sequence. We'll do a little reminder, and if you don't remember this super well, there's a nice description and discussion of this in the back appendix of the book. So we are just going to evaluate this using standard. So we'll evaluate using standard calculus techniques, and really the appropriate one here is we are going to evaluate using what is called Leibniz's rule. So Leibniz's rule. You should have seen this back in your math prereq calc sequence. Leibniz's rule tells us how we can evaluate integrals of these particular forms. If you're just wanting to make a reference back to the book, you can see, for example, you can see what they call math fact. I think it's B.12, and that's somewhere like page 509 in the book, I think is what I have it written down as being. So I would like to go ahead and evaluate that guy using Leibniz's rule. Just a very quick reminder of what Leibniz's rule is. So a reminder, or if you're really rusty, maybe it's a little more than a reminder, but a reminder of Leibniz's rule. So Leibniz's rule, that's not a very good T. Let's try to fix that. Leibniz's rule is something like this. If, right, we have some, I'm going to call it r of alpha, and some function of alpha, and that's equal to an integral of some other function of alpha, let's call it a of alpha in the lower limit, up to some other function of alpha, let's call it b of alpha in the upper limit, of some integrand, we're going to call that little r of alpha and whatever the variable of integration is, x dx. If I'm interested in this guy, Leibniz tells me how to handle it. It does require a few things. It does require that we know something about a of alpha and b of alpha being real and differentiable. So they have to be both real and differentiable in that parameter alpha for this to work, and that we also need r of alpha by x and the derivative with respect to alpha of r alpha by x to be continuous functions of both alpha and x. So there's some conditions for Leibniz to give the result that they do. But if you have some integral of the form, in our particular case here, we're looking at this integral. The result that we're interested in, r is a function of some parameter alpha, is an integral where the limits might depend on that parameter alpha, and that the integrand, right, also depends on that parameter alpha. We would like to be able to handle the derivative of this guy. Leibniz is going to help me do that. So the if statement's done. Then the result that Leibniz gives us is something like this, that the derivative with respect to alpha, right, of that r of alpha cap r of alpha is going to be equal to, and we get a big mess of terms in here, we get a minus r of alpha comma the a alpha, the lower limit of integration, and I'm going to have a d a of alpha with respect to alpha. I'm going to add to that an r of alpha comma b of alpha, right? And I'm going to take the derivative of b of alpha with respect to alpha, and then just one more term in here, so I'm going to have a plus in here, and this is going to be an integral of a of alpha, b of alpha, and I'm going to have the partial of little r alpha by x, right, with respect to alpha, and then I have my dx in there, something along those lines. So this is a little more general case than we actually need for the present example, but that's what Leibniz rules tell us. Again, you can go to the back appendix of the book for a little more context if you're just a little rusty from your calculus. Let's go back and just remind ourselves of what we were trying to accomplish and solve here. So we were looking at what was going to be a more involved example. It's a generalization of example 6.4. We are going to have a known random variable x. We're going to square that and scale it by a positive constant c to create a derived random variable y. We would like to find out what the model is of that. So the probability density function, little f of cap y of y, we would like to find that probability density function of y, and we're going to do it with the Cdf method. In order for us to get that Cdf method started, we know we're interested in the event y less than or equal to little y. We found out what values of x that corresponded to. We can see that through the graph of what relates x to y. It's following a quadratic curve. And so when I write my Cdf expression out, I get my Cdf of y being related to a probability of x being on an interval that goes from minus root y by c to plus root y by c. I can express that as a probability, which I did right here. Once I've got that CDF, the second step of the CDF method is that we differentiate that CDF, and that gives us the probability density function of interest, in this case, the probability density function of y. This is, in our particular case that we're looking at now, we're taking the derivative with respect to y, right, of something of a form that has an integral where the integral limits depend on what it is that we are differentiating with respect to, and then we've also got an argument. In this particular case, the argument is not a function of y, so we're going to see a little bit of a simplification from the general expression that Leibniz gives us. So in order for us to be able to handle that derivative of an integral, we're going to use Leibniz's rule. This is something you can review in your calc books or in the back of the book. I gave a basic reminder of Leibniz. It's talking about if we have that integral expressed, where it could be that both the integral limits and the integrand are a function of that variable of interest alpha, and we are interested in the derivative of that integral. Leibniz just tells us exactly what that expression should be like. It involves the integrand, right, and some partials with respect to the upper and lower limits, and then an integral that just has something to do with that original integrand as well. All right, so let's go and think about this in terms of the present case where we are trying to find our PDF of Fy. So going back up here one more time, we're going to just look at it. We can see that my Fy of interest that I have, right, is this guy over here. Let me copy that down so that we can have that near our result of Leibniz, something along those lines. So we were looking in this particular case of what? We had an Fy of y, right? That is our desired probability density function that we are taking a look for in this particular case, and it should be a d dy, right, of my Fy of y, which is a d dy, right? And in that particular case, it was an integral then, minus root y by c to root y by c, and then I'm going to have my fx of x dx. I think I got that right. So for us to be able to find the probability density function Fy of y, all we need to do at this point is identify which pieces correspond to those things from Leibniz. So I'm going to go ahead and use the notation we had from Leibniz. It had a capital R. The capital R in our case is cap F of y. We had in Leibniz a parameter alpha. Well, in our case, that is just y. We had this idea of a lower limit that could be a function of whatever that parameter was. In our case, that is a minus root y by c. We had an upper limit that by Leibniz's notation, the one from the book, was b of alpha. In our particular case, that is a root y by c. We also have the integrand. We called that r of, if you remember, I think in here it was alpha comma x. Alpha comma x. In our particular case, this is going to be fx of x, which is not, right? It is not a function of the parameter alpha equaling y. So we will need to use that particular restriction on our case. It'll simplify our results. So now I just need to plug these guys in there. Okay, so in this particular case, we already know that we were looking for, if I just remind us where we're at in this, we're looking for Fy of y. So I'm going to repeat that down here as well. I'm looking for my Fy of y, and that ddy of that mess, the integral of minus root y by c to root y by c fx of x dx, we know from Leibniz should have three pieces, right? Those three pieces in our particular case are the ones that are based on those integral limits, and then the one that has to do with an integral of the partial of the integrand, and that partial is taken with respect to the parameter alpha, which in our case is y. Since little r is not a function of y in our particular case, that partial will give us 0. We'll have an integral of 0. That term is not going to show up at all. So we only have those first two terms that are going to come into play in our solution in this particular example. So if I go ahead and do that, I know that we were looking for, what was it, a d dy of Fy of y, and Leibniz says we can get three terms of there. We know one of those is 0, and I just plug in the above parameters up here and use Leibniz's result, and I get a minus f sub x of minus root y by c, right? And I'm going to have a d dy, because I have to differentiate with respect to that parameter, and I'm going to get a minus root y by c. That's the first term, plus an fx of root y by c, and I need to differentiate that d dy of, in this case, root y by c, something along those lines. Okay, so I'm going to clean this all up, put it into a single expression, and we should be done. Fy of y, our desired probability density function for a derived random variable y, is going to be equal to an fx of root y by c, right? And I'm going to have a plus f sub x of minus root y by c. How did I get that? Well, the minus sign that I see over here is actually going to get canceled with the minus sign there. So they're both going to have a plus sign on there. And both then will have still that part that is differentiation with respect to y of root y by c. That derivative type of term is going to end up giving me, in this particular case, let's just do a little side calculation. I need to do a d dy, right, of root y by c. That's a 1 over root c, and I'm going to do d dy of root y, which is a 1 by root c. The derivative with respect to y of the square root of y is going to be 1 over the square root of y, something along those lines. So in this particular case, I can have those guys come together in a nice way. They would end up, if I can get my piece here to cooperate, a 1 by root cy. I'm missing a term in here. So if we had this one, this is what, a y to 1/2. I need to multiply. This is going to also have a 1/2 term in it. So I'm going to get a 2 outside there as well. Okay, so I should be all good to go. Derivative of y to the 1/2 is going to be a 1/2, right? Y to the minus 1/2, which is a 1 over 2 root y. So that's how I got that combined with the root c over here. Okay, we are actually super close at this point. So just needed to finish this out. This whole thing's going to be divided by then what? This result here, this 2 root cy. I think this is deserving one more cleanup. I'm going to get it really nice and neat. Fy of y is equal in this case to fx of root y by c plus and fx of minus root y by c all over, and we are going to have a 2 root cy. And that really was what? Y greater than equal to 0, something along those lines. There probably is a complementary piece in here. We know y could never be less than 0. So for less than 0, the probability density function had better be 0, something along those lines. So if we wanted to know if this generalized result has a chance of being right, one of the things we could do is we could use this generalized result that we just derived and see if we can get the particular result that was part of the book exercise 6.4. So let's check, and then we'll be done with this lecture. Let's check our result. Right? With the specific case, that we find in the book example 6.4, something along those lines. In that particular book example, what we find is that scaling coefficient was just c equaling 1, and that the original distribution x was distributed as a uniform -1 to 3. So it was a 4-wide uniform distribution. So it would have had a probability density function that was a fourth all the way across. We'll go ahead and write that out. So we know in this particular case, fx of x, right, is equal to, it's going to be a 1/4 for -1 less than equal to x less than or equal to 3, and it's a 0 otherwise. Okay. If we are interested in finding our fy of y, we said here f my y, right, is in this particular case going to be c times x squared. C was 1, so it's just going to be an x squared. We're looking for the distribution on y when we square x. We just need to use the result that we had previously obtained. This one's sitting up here. A little bit that might help us on this as well is just thinking a little bit about this fx. Let me just do a very quick sketch of this as well. Going from -1, then 1, 2, 3, right? And I've got a value of 1/4 on that. Not getting this as clear as I want. Let's try this once more. Get a 1/4 in there. This is my fx of x as a function of x, something along those lines. Think about what happens here when I square x. There's a couple of values, right, from -1 to 1, that when squared, I get contribution from both the left-hand side and the right-hand side. But any x that goes from 2 to 3, right, I'm going to get the contribution here from the positive x, but there was nothing over there that's going to contribute to that. We're going to see this come through when we get our final result in this particular case. So let's see what we can do with this. Going back to the general result we got, we knew that we needed an fx of root y by c. We need an fx minus root y by c, right? And then we have that overall scale factor going on in there as well. So the first thing that I need to be concerned about or making sure that I've got is I'm going to need fx of root y by c, but c is just 1, so that's a root y. I need to be able to handle that guy. And that's going to be equal to what? It's going to be equal to a 1/4 for 0 less than or equal to root y less than or equal to 3, right? We know y was always non-negative, and so we should be looking over a range that's non-negative, and we would get 0 other y's. These values of root y going between 0 and 3 translate over to a 0 less than or equal to y less than or equal to 9, something along those lines. If I wanted to look at the other half of what Leibniz's rule gave me, I need to get this as an fx of minus root y, something along those lines. So f of x for negative values, f of x could either only be 1/4 or 0. That's all it can be. We've seen that over here. When we looked at f of x, right, it is a value of 1/4. That's all it can be. And it goes from a range of -1 to 3. We just handled with fx of plus root y. We handled this guy right here from 0 to 3. Now we're going to be handling this other part for negative values, and that's going to go 0 to -1, something along those lines. So I look at fx of minus some number, some real number, because y always has to be positive. In this particular case, then, I'm going to get, again, just 1/4, and that's for 0 less than or equal to root y. C is 1, so it's just not going to show up in this. And then I'm going to have less than or equal to, in this particular case, 1, something along those lines. That goes off and translates to a 0 less than or equal to y less than or equal to 1, and it's 0 otherwise. Just square both sides of that guy, you get it, just as you would expect. So when I add these guys together, what do I get? I'm going to get my fy of y, and that is going to be equal to, I need to be able to add my fx of root y and my fx of minus root y, and I need to be able to divide those guys, right? If we go back up here a little bit, by 2 root cy, which is going to be 2 root y in our particular case. So if I take a look at these two pieces I'm adding together, they share some space, right? They both have something goes 0 to 1. This fx of minus root y goes from 0 to 1, and there's a portion of fx of root y that goes 0 to 1 as well. So those guys are going to add just no problem together over that, and I would get 1/4, and 1/4 is going to be 1/8 divided by 2 root y. That's gonna be this 1/4 root y, something along those lines. So I'm going to get 1/4 root y in this first case. That's for 0 less than or equal to y less than or equal to 1. Okay. The second one that I have in here is going to be just contributing from this first term, fx of root y. So that's this guy. That's the only thing that goes out from 1 to 9. So that guy's going to be all by himself. And we are going to end up getting a 1/4 plus 0 over 2 root y. That's going to give me a 1/8 root y for 1 less than or equal to y less than or equal to 9, and it's 0 otherwise, something along those lines. So just a reminder, very quick, how we got this. If you take a look at my fy of y, we know that if we go back to our previous results, that fy of y, right, had a couple of pieces being added together, fx of minus root y by c plus fx of minus root y by c, all divided by 2 root yc. C here is 1, so we're just going to start ignoring those guys. And I needed to deal with those two pieces. In this first case, the fx root y, that's just from f of x. It is a choice of being 1/4 or 0. And root y is always going to be a positive number. And we can see that range sitting over here in the range space of what x is. That goes between 0 and 3. So our argument, root y, is going to go between 0 and 3. That translates to y going between 0 and 9. And they have to have that value of 1/4. That's all that y, that fxy or fx root y can be. 0 otherwise, no problem on that. This fx of minus root y, again, root y is a positive number because y is always positive, so the minus root y is always a negative number. The only values that are negative that have a non-zero PDF value for fx is going on that other range, which is that 0 to -1, something along those lines. And so we're going to get a 1/4 on that, and that's for y going 0 to 1. Well, you get the minus sign on there, and that's what got us to the other side of that PDF on x. Square both sides of that, and that's just going to be 0 to 1. The overlap of these two functions, fx of minus root y and fx of root y, is only over the interval 0 to 1. So I'm going to get 1/4 and 1/4. That's 1/2 divided by 2 root y. That's going to give me a 1/4 root y. That was this first piece right here for the interval 0 to 1, where they're both contributing non-zero content. The other case that we're going to get in there is where f of x root y is not equal to 0, and f of x minus root y is equal to 0. When those two guys get summed together, I get this second piece down here. That's going to be a 1/4 plus 0 over 2 root y. That's going to be 1 over 8 root y. And that's for all those cases that were only shared by the first term, not the second term. 1 less than equal y less than or equal to 9. This matches just fine the result in the book off of that example 6.4. And so it does give us some pretty good confidence that our generalized result that we had done before is the correct one. Next lecture, we're going to be talking conditional probabilities with continuous random variables.